Welcome to lecture 8. In this lecture, we make some observations on the row reduced echelon form of a matrix. So the first observation is, suppose you look at the elementary matrices, the matrices corresponding to the elementary row operations. It can be easily seen that they are indeed invertible. You can see that it's inverse Eij if Eij is the matrix that corresponds to the operation of swapping two rows, I and j, ij and ith and jth rows. Then it is its own inverse. If you look at the matrix E alpha I, alpha is non-zero, that is the ith row is being multiplied by alpha, then its inverse is E of 1 by alpha I. That means multiplying the identity matrix, the ith row of the identity matrix by 1 by alpha, and E of minus alpha ij is the inverse of E alpha ij. So that means if you take all these elementary matrices, they are invertible, therefore their products are invertible. Now the question is whether the converse is true. That means given any invertible matrix, is it a product of elementary matrices? Suppose I start with an invertible matrix A. Now I have a matrix A inverse. Do a lot of elementary row operations and bring it to the row reduced echelon form. So when we do this row reduced echelon, when we do this elementary row operations, what we do is we do multiply on the left by a lot of elementary matrices. So take this product of elementary matrices as E and write the row reduced echelon form of A inverse in the form E times A inverse. So E A inverse is the row reduced echelon form of A inverse. Now suppose E A inverse has a 0 row. That has to be down below. If that has a 0 row, now you multiply EA inverse to any other matrix B on the right. EA inverse times B will also have a 0 row. In particular, EA inverse times A will have a 0 row. But now using associativity of matrix multiplication, we can write that E times A inverse A has a 0 row, but E times A inverse A is identity, therefore E has a 0 row. But E is product of elementary matrices, all of them are invertible, therefore E is invertible, hence E cannot have a 0 row. Therefore E A inverse does not have a 0 row. This implies that each row in the square matrix E A inverse has a pivot, but the only square matrix in row reduced echelon form having a pivot in each row is the identity matrix. This says that E A inverse is equal to I. That is, A is equal to E. And what was E? A product of elementary matrices. So what we have proved is, if A is invertible, then A is a product of elementary matrices. So therefore, the theorem is that any square matrix is invertible if and only if it is a product of elementary matrices. Now you start with an m by n matrix. You apply several elementary row operations to get to a row reduced echelon form. Okay. Now I apply my logic to with a sequence of algorithm to bring it to row reduced echelon form. You may be having a different sequence. So the question is whether ultimately you will get the same row reduced echelon form. I may have a row reduced echelon form, you may have a row reduced echelon form. Is that possible? In fact, we have a theorem which says that given any m by n matrix, there exists a unique matrix in Fm cross n in row reduced echelon form obtained from A by elementary row operations. So whatever row operations you do, it doesn't matter, once your matrix reaches row reduced echelon form, this is unique. So this proof uses whatever we have discussed earlier, that elementary matrices are invertible and their inverses are also elementary matrices. Moreover, it uses the fact that each invertible matrix is a product of elementary matrices that we proved just now. We will not, the proof is little longer and it is elementary, it is not difficult at all. It is given in the lecture notes, which is uploaded to Moodle page. It's been there. So please refer to the notes and understand the proof. Given you start with any matrix, start with the matrix A, you apply any algorithm of your wish and I apply any algorithm of my wish to bring A to a row reduced echelon form. The theorem says that the row reduced echelon form is unique. Okay, so now let's make a few more observations which will be useful later. For that, first let us set up some notation. Suppose A is an m by n matrix and it has been reduced to its row reduced echelon form. So in that form there will be a certain number of non-zero rows and certain number of columns. So let Ri1, Ri2 up to Rir be the rows of A which have become non-zero rows. That means all these contain pivotal entries and the remaining rows are all 0. Okay, so these are the non-zero entries and the remaining rows are 0. Suppose Cj1, Cj2 up to Cjr for J1 less than J2 up to less than Jr be the columns of A which have become pivotal columns in RREF. That means these are the columns that contain the pivotal entries. So let us make some observation with this notation being set. All rows of A other than RI1 up to RIR are linear combinations of RI1 up to RIR. So what you see is that the rest of the rows will be linear combinations of these rows. The columns Cj1 up to Cjr, they are nothing but the standard basis vectors E1 up to ER, and all columns of A other than Cj1 up to Cjr are linear combinations of Cj1 up to Cjr. In fact, you can say little more in this direction. Suppose I take the first k pivotal columns, E1, E2 up to Ek are all the pivotal columns in RREF that occur to the left of non-pivotal column. Then the non-pivotal column is of the form A1, A2 up to Ak and the rest of them 0, transpose of this. So therefore what we can see is that if a column C in A has become this non-pivotal column in RREF, then C is nothing but linear combination of the k pivotal columns that occur previously. So if I have a column which occur after the kth pivotal column, this is nothing but the linear combination of previous k pivotal columns. That's the observation. It's a refinement of the observation 3. And if A is a square matrix, then A is invertible if and only if RREF is identity. In fact, that this is something that you can it again follows from our previous theorem as well. Let's look at one example. This is the same example that we the same example that we considered in the previous lecture. So A is this given matrix, and using several elementary row operations we have transferred it to a row reduced echelon form. So now there is a 0 row at the bottom. So therefore the row corresponding to 0 row, that means 2, 8, 7, 9, that is a linear combination of the previous 3 rows. In fact, that is easy to see because that becomes 0 by doing elementary row operations, and that says that it is a linear combination of the previous rows. The pivoted columns in RREF are E1, E2, E3. Now you can see that the third column is a linear combination of first and second column. And there is the fourth column, which is E3. So this concludes our this lecture on observations on RREF. We will come back with more properties and applications of row reduced echelon form in the future lectures.